Hi everyone, my name is Hang Liu. I'd like to present our research on a new network architecture called Effective-Centric Networking. As you know, the emerging mobile and IoT applications involve the interaction of users and the smart device. Users communicate with the device to affect them to conduct in the desired way for satisfying users' needs. Traditional communication networks mainly focus on how to reliable and effectively transmit bits or packets. This paper proposes a new network architecture, Effective-Centric Communication Networking, ECN. A user sends an order to one or more targeted nodes in ECN whose location and identities may be unknown in advance to generate the effect on the node and instruct the node to act. An order contains instruction code and data. Actually, according to Shannon and Weaver's foundational work, communications problems could be classified into three levels. The first level is transmission of symbols. The second level is semantic convergence of transmitted symbol. That is, semantic information transferred by the sender and the meaning interpreted at the receiver. The third level is effects of conveyed semantic information. That is, the effectiveness of communication to affect conduct and generate effects at the receiver in a way desired by the sender. In the past decades, research has focused on reliable and effective transmission of base, symbol, or packets. More recently, semantic communication have received some research interest. It concerns transmission accuracy of the meaning of the data rather than the correctness of the base or packets, which can enhance communication reliability, especially in challenging channel environments with high beta error rate. It can also achieve high data compression ratio by filtering out unimportant semantic information. Considering emerging IoT applications, the goal is to affect the target receiver to perform certain conduct in a desired way. So user may push some machine learning model to affect the target node's conduct or instruct the target node to perform some task or request target node to send information. Traditionally, IoT devices are pre-provisioned, but this device become more powerful and multi-modal. So it's desirable to control and interact with them at runtime. A process on a machine conventionally invokes a procedure on another machine based on middleware, which needs to resolve the host address and port. It's challenging to handle mobility, intermittent connectivity, and service migration. So it's essential to dynamically select and configure service to perform desired tasks for the user. That's why we propose effect-centric networking. ECN focus on effects of communication. The goal is to form a self-organized and self-optimized cooperative programmable computing network to perform in-network processing and realize the desired effect by leveraging integrated communication, computing, and storage. So users send not only data, but instruction code in messages to generate effect, affecting the network node conduct. Select the service node in the network based on the instruction code carried in the message. So here I show a message format in ECN. So an order message contains service ID, order number, instruction code, payload, signature, certificate. So the service ID identifies the service requested or provided by user. For example, computation service, object recognition, or information service, processing, and retrieving content. So instruction code give more detailed instruction how to handle the message. For example, detect a car with a specific license plate number, recognize the object, and add related information from a trusted database. Obtain the average temperature in a building or transcode a specific content to a specific format. Here are just some examples. So in ECN, message routing is two-level. So a message is forwarded to the node that can handle the instruction code carrying the message according to the service ID. Then the node evaluates the instruction node in the message and take a further action to select the optimal node for actual execution of the order. Then the user order is executed at the selected execution node to get the result. The result may be synchronously or asynchronously sent back to the original user as a response. So different routing algorithms can be used. For example, service ID publishing, or distributed hash table, lookup with service ID resolution, server, etc. So the instruction code in the message provides further instruction for order execution. So this two-level routing allows flexible selection of the order execution node and the message forwarding paths in ECN network to optimize network performance and satisfy the need of the user with a certain scalability. Different message delivery schemes on the data plan are supported, including unicast, multicast, anycast, delayed message or dropped message in the network. To demonstrate how ECN works, I'd like to give you an example. So a user sends an order with instruction code to apply an updated machine learning model to locate a vehicle with a specific license plate number and obtain related information such as traffic and weather information in an ECN-based smart city network that consists of various edge nodes and camera sensors. So here it shows the message. The service ID is computation service, traffic monitoring. Instruction code indicate to update the machine learning model and find the vehicle. The payload here in the order is the updated machine learning model. So user send this order to the network. So the network forward the message to a node that can handle monitoring service based on service ID routing. So in the figure, the node A can handle traffic monitoring service. So node A receives the order, so it evaluates the instruction code in the message and select the order execution node. So node A may decide to execute the order by itself if it has enough resource. Node A may not have license plate recognition program. Then the node A can fetch the license plate recognition program from a repository by sending an order to the repository. Then, after it fetched the program, it can execute the order. Alternatively, node A know another node, node B already has license plate recognition program. Then it can forward the order to node B. Then node B can conduct license plate recognition by ask the camera sensors to send the video stream to node B. So in general, the nodes in an ECN network can evaluate the instruction code, then retrieve the order execution program and the related data, execute the order, or distribute the order tasks and orchestrate the order execution on a set of distributed nodes with virtual machines.